Hello everyone, and welcome to the Circle Post Lab, the first post lab of the year. This is where we are going to review what you found while doing the Circle Lab and graphing the Circle Lab, and then we're going to put it all together, right, and make sure that we are all together on what we found, right, and what it means. Sometimes in these post labs we will add new terminology, give names to things that are important. Sometimes we will use it to build upon as we kind of go into the rest of the unit. So in this lab, you measured the circumference and the diameter of 6 different circles, and you graphed them, with the circumference measured in centimeters on the vertical axis and the diameter measured in centimeters on the horizontal axis. Notice here I am using symbols instead of the words, which is okay. You can certainly write out the words circumference and diameter. That's the way the program graphical analysis does it. If you're going to use symbols, though, pick some symbols that are meaningful. Right? Don't use X and Y all the time. That's what we do in math class. But in here, that would get awful confusing if every graph we made was X and Y. So we'll pick things that are meaningful. Diameter, a capital D. Circumference, a capital C. If you decide to use symbols and later on I tell you, well, this is the actual accepted symbol, that's okay. Right? Eventually you'll figure out the way that the correct language to use, the correct way to write it. So, come up with a symbol when you're working on your lab sheet and use that, right, instead of the words. So when you graphed that, I'm hoping that your graph ended up looking pretty much like this. A nice linear graph that went through 0, 0. Well, what does that tell us about the relationship between the circumference and the diameter? Well, as we've discussed in other movies, if you get a linear graph that goes through 0, 0, if we look at a circle with twice the diameter, in order for the graph to stay linear, we'd have to have twice the circumference. 3 times the diameter would have to have 3 times the circumference. If they weren't changing the same, the graph wouldn't be linear and go through 0, 0. So what do we call that? We call that a proportionality. So this little statement here is read as circumference is proportional to the diameter. Right? This is the proportionality symbol. Notice here again, I'm writing it in symbols. Sure, you could write out words, right? But as a matter of language here, we could write it as a capital C and a capital D. Now this is a powerful thing to know about circles. It allows us to compare one circle to the other, right? Proportionally speaking. But it's not as powerful as it could be because it doesn't allow us to make direct predictions like if I have a circle of this diameter, it'll have this circumference and vice versa. For that, we need a math model. And since this is a linear graph, we can use our old friend y equals mx plus b to build a math model of this linear graph. Now, we're not going to use y and x. Right? We're going to use symbols that are more meaningful. And we're not going to use m and b. We're going to use numbers that are actually quantities that are actually from our lab. So first off, what should the y variable be? And by that I mean, what are we graphing on the vertical axis? Well, we're graphing circumference on the vertical axis. So the symbol for that would be C, capital C. This is the slope. So what should the slope be? Well, certainly on your lab sheet, you hopefully plugged in the slope you got from graphical analysis, but we did something even more powerful. Right? I asked you to enter your slope into the Google form. So let's look at these. This year, because you were all working individually, we have lots and lots and lots of slopes. Look at them all. Okay? We ended up with 96 people prior to this morning putting in their data. Take a look at all those slopes. Do you see how close they all are to one another? There is not a lot of variance. Right? This is a special number. Everybody basically got the same number. I mean, look at the first digits. I believe there's only 2 on this whole list that aren't a 3. Hey, here's one. There's a 2.9. I think there might be one other somewhere in here. Right? So we can be pretty confident that this first digit is a 3. The second digit, we start getting a little more variance. We're seeing a lot of 1s. Oh, here's a 0. Here's a 2. A couple more 2s, a 1, a 2. Here somebody just rounded off to 3. We'll talk about that with significant figures. Some more zeros, right? And then once we get past a couple of digits, then we're starting to get just kind of random things seemingly in there. So notice here, I took an average. And overall, for my 5 hours of honors physics, for everybody that got done with this part up till now, the 96 people, right, we have a class average of 3.13. Does that sound pretty close to something familiar? Hold on. We'll get there. Okay? Now, I'm not going to use all 3 digits here. I'm just going to use the first couple because that seems to be, what we're most sure of in our data before we start getting out into the kind of the 3rd and 4th digits. And we're going to eventually start talking here in the next few days about how many digits should you have typed in here. Because we had anywhere from 4, which is probably what the computer told you. Here's 2, right? And we even saw a few that only put 1 digit in. That seems weird, right? So we'll talk about how many digits you should put in. It's something called significant figures. So going back here, I'm going to plug in a class average of about 3.1. Again, you can put yours in, right? It'll be your specific math model. And certainly that's what I expected you to do on your lab sheet. Now, in order to interpret what this means, we need units. How do we find a slope? Rise over run. So that's how we find the units. The units of rise are centimeters. The units of run are centimeters. That's pretty strange that you get the same unit. We'll talk about what that means in a moment here. But now it comes time to interpret this. You've practiced this a bit in a concept builder. We want to write a for every statement. Right? Remember that slopes are rates of change. Slopes tell you how much does your y variable change when your x variable changes. In this case, how much does your circumference change when your diameter changes a certain amount. Okay? So look at this number, and hopefully you came up with something like this. For every 1 centimeter of diameter, what happened to the circumference? It increased by, on average, about 3.1 centimeters. So hopefully you have something like this on your lab sheet. If not, you might want to add this in. Right? For every additional 1 centimeter of diameter, the circumference increases by 3.1 centimeters. For every one of these, you get 3.1 of those, right, is basically what this is saying. This is an important thing. Sometimes in our labs, the whole point of doing the lab is the slope. All right. Sometimes, like in this lab, it's the whole math model. But sometimes I really just want to understand what the slope means. So slopes are very important in here. All right. And it's not just rise over run. That's what they mean in math. How much up and how much over are you going on the graph between 2 points? Right. It's what does that slope physically tell you about what we're graphing? And that changes depending on what we're graphing. Okay, so this is the y equals m part here. All right. Now, here's something weird that happens, if you notice that. We have centimeters per centimeter as our units. But remember, this line means divide. What happens when you divide something by itself? What's 10 divided by 10? What's 100 divided by 100? What's 250 divided by 250? It's 1. Right? So a centimeter divided by a centimeter actually reduces down to 1, and you don't have to multiply by 1. It's the multiplicative identity. So we tend to write this slope, this special number, without units. It's one of the few numbers we're going to come across in this class that we don't use units. But remember, there technically are units on it. They just happen to cancel out. And so it helps you to remember what it means to remember that there are units. One of the interesting things about this is this number would stay the same no matter what we measured it in. If people had used inches, they would have gotten something like 3.1 inch per inch, 3.1 foot per foot, 3.1 meter per meter. As long as you measured the diameter and the circumference in the same units, you're going to get the exact same number, right? And the units will still cancel. It's a very special little number. So that's our y equals m. What's our x? Well, that's what we graph on the horizontal axis. So that's the diameter. And now we need to talk about b, or the y-intercept. So you may remember here that for the y-intercept, there's two tests we have to use to decide whether or not it's significant, by which I mean whether or not we say it's 0. The first is a test of logic. What would it mean if this point was actually 0, 0? Now, I don't mean what does it mean mathematically. Right? Mathematically, it means, well, the line goes through 0, 0. But what does that physically tell you, given that this is a graph of circumference versus diameter? If you have a 0, 0 point, it means if the diameter is 0, then that means the circumference has to be, exactly. It means if the diameter is 0, the circumference has to be 0 centimeters. This is, when I ask on a lab sheet, what does your y-intercept mean? This is what I'm looking for. Not what does it mean on the graph, not what does it mean in math class, but physically, what does it tell you about what we are examining, about the variables that we're testing, right? About our relationship. So it tells us that when the diameter is 0, the circumference is 0. Now, does that make logical sense? I hope so. If you keep shrinking and shrinking and shrinking a circle down to a dot, right, so it doesn't have a diameter, well, it also doesn't have a circumference. So it makes logical sense we should have 0, 0. However, my guess is that nobody actually got 0, 0 on graphical analysis. It's almost impossible to statistically end up, when you do a linear regression, a linear fit, on a program like that, to have it actually spit out 0, 0 to, 4 or 5 decimal places. Okay? So you probably got some small number. So logically it should be 0, 0. But remember, we've also got a quick and dirty statistical test called the 5% rule. Again, this is not great stats, right? This is not something you'd use in AP stats. You become an engineer, you will not use the 5% rule, or you'll get fired, right? You'll use more complex statistical analysis like error bars and standard deviations and different things like that. Okay? But in here, it'll work for what we do, because we're inside of a classroom and we don't have wild ranges and things like that. So it says, take 5% of your maximum y value and compare it to your y-intercept. So our y value here is the circumference. I assume your maximum y is about 128 centimeters, give or take a little bit. Was about when I measured it. So 5% of that, multiplied by 0.05, is about 6.4 centimeters. Notice y-intercept has units of the y-axis. Right? So now compare your y-intercept. And don't worry about the positive or negative, right? That's just above or below 0. You don't need to worry about that in this case. Was it smaller than 6.4? My guess is it was way smaller than 6.4. I doubt anybody was even remotely close to 6.4. So in other words then, since it was way smaller than 5% of our maximum y value, we're going to say, you know what? Close enough. It's negligible. The root of that is neglect. We can neglect it. So we're going to say, you know what? It's close enough. We're going to call it 0. Now, the only issue you have is if these two tests conflict. If one says one thing and one says the other, we got a problem. Right? Hopefully, if we've done our labs carefully, right, these two things should match up. Right? Your logic should say 0, 0 works or doesn't. Your 5% rules should say, well, y-intercept works or doesn't. It's when they don't that we have to do a little more thinking. But hopefully in here, things will work. So since it's a plus, and if we're going to call it 0, you don't have to add 0. So there is our specific math model. And I call it specific because it has your slope in here. Yeah, I've got the class average, right? But it's your slope. With this math model, right, we can make predictions. But let's make that math model a little bit bigger. Because as I've been mentioning here, this slope is not just some random number. Sometimes our slopes just kind of depend on how we set up the equipment. Right? So it might vary from even table to table in the room. Right? From group to group might get different slopes. And that's okay because their equipment was set up differently. Right? But in this case, this number was pretty much the same for, I think, 96 different people, right? Almost got the exact same slope. So this is a very special slope. Hopefully, you've noticed that. Right? What does it look like? Remember, we got an average of 3.13. That is really close to a very special number. Remember what that number is? It's so special, we have given it its own name and its own symbol to use as part of the language. It is, of course, pi, right? Denoted by this lowercase Greek pi. To 3 sig figs, and if you don't know what that means, we'll get there in the next few days, pi is 3.14. I bet there are people watching that know pi to several more decimal places. It's a weird little number. It is non-repeating and non-terminating, which means that, we've had computers calculate this out in very modern ways to tons and millions of digits, and it never repeats itself, and it never just terminates to zeros. Very interesting little number, and a number which exists in nature. So let's give this a definition. Right? From our graph, we can see that pi is the slope of a graph of circumference versus diameter. Right? That's where we just discovered pi. I didn't tell you pi. We saw it happen in nature. In math, you define it more often as the ratio of the circumference to the diameter. If you move the diameter to the other side by division, right, you get circumference over diameter is essentially pi, the slope of the graph. You should be able to take any circle, measure its circumference, measure its diameter, put them in a ratio, and get this number. In fact, pi was first discovered by the ancient Greeks. Right? They were great geometers, and that's kind of how they figured out what pi was. They actually took a rope with stakes on the end of the rope. Okay? So that rope was technically the radius, but if you double it, it's the diameter. So they stuck one stake in the ground in the sand. They took the other stake, stretched the rope out, and inscribed a circle. Then they took that rope off, doubled it so they had the diameter, and they laid it in that circle. And they found that if you laid that diameter in the circle, you could fit 3 and a little bit more. Right? So the Greeks thought that pi was a number a little bit above 3. And throughout history, we've been refining ways of calculating pi. And like I said earlier, now we do it with computers. It's very fancy. We can take it out to many, 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 many decimal places, right, and get really precise, depending on how precise you want to be when you're using it. Right? But this is a number that's been known since antiquity. Right? Anytime you see pi show up in an equation, it usually means that something circular or spherical, if we're in 3 dimensions, is involved. The propagation of water waves when you drop a rock in a lake, right, in a still pond or something. Right? We see those circular waves go out. Right? And in those equations for those waves, pi pops up. Right? You start talking about a sphere, pi's going to pop up. Right? I mean, all sorts of things. So pi here, this new number that we've discovered, right, in lab, is it's a very special number that often relates things with circles and spheres, and other roundish kind of things like ellipses and other things like that. Right? So if we take pi, this is something I used to have people do when I had them write up lab reports, which I don't do anymore. I just have you do the lab sheet. Aren't you happy? I used to have them calculate a percent error in cases in labs like this where we actually know what the slope is supposed to be, right? Which won't always be true, but in this case we do. It's often nice to figure out how far off were we. So if you take your theoretical value for pi, you put in your experimental value for pi, and you divide by the theoretical value times 100 to turn it into a percent, you can see how far off we were. Now, notice here, to 2 sig figs, 2 digits in this case, 3.1, we had 0% error as a class. Even to 3 sig figs, 3.14 is the given value for pi, we ended up with 3.13. If you plug 3.14 in for the theoretical, 3.13 for the experimental times 100, you get 0.3% error. Not 3%, 0.3% error. And when you think about how we did this lab with nothing more than cake rounds and a measuring tape, it's pretty amazing that we can get to that level of precision, right, in our lab situation. I can give you any fancy equipment here, right? And yet we could do that. Part of that is the power of averaging, right? Some of you will get slightly bigger errors, right? We saw a 2.9. That might be a couple of percent error. We saw a 3.3. Again, that might be a 2 or 3% error, which still is not a lot of error, right? That's still an error that you would celebrate in some of your other science classes, right? But if you notice here on average, we are extremely close to even 3 digits of pi. So if we take pi and we plug it into the math model, we get circumference is pi times the diameter, and that's what I like to call a general math model. Okay? Hopefully you're taking notes at this point, right? And this is something, this kind of thing and this kind of thing you would write in. Maybe you have room on your lab sheet. Maybe you have your separate paper and you're writing this in. A lot of this other stuff is on your lab sheet, right? Like the graph and the slope meaning and stuff like that. But new stuff, right, need to get in your notes. So this is a general math model. And the power of a math model is as a predictive, descriptive tool. Now, we don't need the graph. We don't need to do another lab. We've done one. We've proven it experimentally, right? We can now say, okay, with pretty good confidence, that if we have the diameter of a circle, we can calculate its circumference. And vice versa. If we know the circumference, we can do one step of algebra, divide by the diameter, and we can calculate, divide by pi, right? And we can calculate the diameter of the circle. Right? So we can figure these things out by using this math model. And the point of doing the lab is to discover this, to construct it, if you will, ourselves, so that we have greater buy-in, right? And we see that this is something that exists in nature. It's not just something I'm telling you, right? All I'm using is math that you already know, right? And the results of your lab, right, to come up with this math model. This is something we are going to do over and over and over again this year, right, in order to construct our physics knowledge, right, from observations of nature. Now, one little extra thing. Sometimes you might already know the equation, but sometimes this equation is written in terms of a different quantity. That quantity is known as the radius, which I've mentioned, right? The radius is the distance from the center to the edge of a circle. How many radii are there in a single diameter? And yes, the plural of radius is radii. Right? There are, of course, 2, right? One diameter is 2 times the radius. It's 2 radii. If we plug that in for our diameter, I love that, right? Plug it in right there, right? Then we get an adjusted general math model that we can calculate the circumference of a circle by taking pi times the diameter or 2 pi times the radius. That's why those 2 equations, right, are related to one another. It's just a different statement in terms of radius or diameter. Now notice, I could have done this lab in terms of radius instead of diameter. Probably would have been easier, right, given that I had marked the center of the circle on each one of those, that you could have measured the radius. But if we had done that, what would our slope have been? Take a second and think about that. If we had made a graph of circumference versus radius, given this math model now, what would our slope have been? Hopefully you're saying, oh, our slope when we did circumference and diameter was pi. So our slope if we did circumference and radius would be 2 pi. Be basically 6.28. Right? And the reason I didn't do it that way is because I didn't think anybody in here would see 6.2-ish, 6.3, and go, hey, that's 2 times pi. Right? Wouldn't expect you to get that right out of the number. So I chose a version of the lab where pi, right, would end up being our slope so that we could construct it together. So here is our post lab. This is a very similar post lab to things that we do. Notice the way we deal with symbols. When we need a new symbol, we give something a new symbol, a new variable. When we need a new name, we wanted to name the slope, so we gave it a name, pi. Right? We even gave that slope a symbol in this case because it's so special and useful. Right? And that's how we do things in here. You won't see me do vocab lists and things like that. Right? It's all when we need something, we give it a name. Right? It's always contextual. So I hope you enjoyed the circle post lab, our first one of the year.